Hello everyone, and welcome to Physics Society, and welcome to the second talk this Hillary term. My name is Gia, and I'm the president. We're joined by members of the committee, Rob and Roxanne and Yaquan at the door. Welcome all, and I'm delighted to introduce you to this week's speaker, Myles, for his talk on equations and equality, the physics of climate in a populist world. Thank you.
Thanks. Thank you. Yeah, it's great to talk to the Physics Society. I have spoken to you before, but probably not to any of you individually, because I think it was a little while ago. I wanted to talk about the application of physicists' thinking to political discussions, which may be not something that you've necessarily thought about. I don't know if anybody in this room has even contemplated going anywhere near politics. In fact, the way politics is today, you'd probably run for the hills rather than getting anywhere close to it. But what I'd like you to think about is whether as it were, the unpleasantness of much of politics at the moment might be something we as physicists could do something about, that we could actually help make the world a less divided place. And I'm going to maybe it seems rather quixotic, but I'm thinking that if more of the world thought as physicists do, as particularly the kind of thinking we do in Oxford physics, the sort of very reductive approach to physics that we take here in Oxford, maybe we'd be able to bridge some of the increasingly large gaps in politics today. The particular topic, of course, I'm talking about is what I've devoted my career to, physics of climate, understanding climate and climate change. And I just wanted to start off, just for a bit of inspiration for the talk. I don't know if you've ever noticed as you go through the RER, the local tube station in Paris after you get off the Eurostar, if you go down to the RER station down in underneath the Gare du Nord, you see a bunch of equations up on the wall, and they're rather mysterious. You sort of go through them, they all look like this. And in case you don't understand French, they actually have some English translations there as well. And some of them may look slightly familiar to you if you've done C5, but they're sort of all a bit weird. Somebody said go vegan on there as well, so they're obviously getting the message. Then here's a hint. Sukuro Manabe, he was a Nobel Prize winner who published the first first quantitative account of how carbon dioxide affects global temperatures in the 1960s. And this is reveal all explanation poster, which tells you what these series of equations is actually all about. It's some equations that this artist, Liam Gillick, a British artist, has been inspired to show you, and this was put up to mark the Paris Climate Conference back in 2015. And it's a powerful tool, and he calls it the logical basis for understanding climate change science. And if you look at the equations, and I once nearly missed the Eurostar train trying to puzzle out, to try and work out what this equation was all about. You see, what's He8? Is this some weird isotope of helium that I've never heard of? And staring at this, you realize if you go back to the online version of Manabe's paper, so the one you can pick up if you Google it, and you drill in, and you discover that the way the font has come through in the online, the saturation vapor pressure, which is conventionally referred to as E sub S, okay, looks a bit like E sub 8. And I think that's probably the explanation of why Liam Gillick introduced this strange quantity in his post. I think this really summarizes the way non-physicists look at what we do. They think, yeah, some clever people over there are doing stuff. And because they're clever people, I don't need to understand it. And he just sort of turned the equations into an artwork without for a moment even asking, I mean, I'm sure he never sent them to anybody, certainly not to any physicist, to say, have I got them right? Because that wasn't the point. And I think this illustrates the challenge we face, that we have, you know, over the 20th century, we slipped into a way of working in politics and in the world where technocrats, technically competent people, were doing their work and making people's lives better, perhaps, and everybody else was expected just to sort of go along and join in. And I think this really came to a head with this incident. Here's Boris Johnson following the science, flanked by two scientists. And even with the coronavirus pandemic, even with a threat as in your face as a global pandemic, people did go along with following the science to start with. And then, as you probably all remember, in most countries at least, the wheels then came off the wagon and it didn't really work. And the problem with climate is that, unlike the coronavirus pandemic, which was evolving over weeks, this is a problem that's evolving over decades, over generations. And just telling people, follow the science, really isn't working. And we're seeing that very, very clearly at the moment with drill, baby, drill in the United States, campaigns saying no to net zero in the UK, Kemi Badenoch saying, I'm not a climate skeptic, I'm a net zero skeptic. Which is like, it's interesting that she can say that and get away with it. Nobody challenged her on it. Yeah? I'm not, you know, it's a bit like saying, I'm not against Ptolemy, I'm just for Copernicus. You know, it's like something like that kind of logic. And even the Labour government, which kind of prides itself on being evidence-driven and so on, they're getting increasingly edgy about talking too much about net zero because they've recognized that it's become politically toxic. And if we actually look at what's going on, sorry to depress you, but this is emissions, global carbon dioxide emissions from fossil fuel use in dark blue and land use change in light blue. You can see that, you know, when we signed the Rio Convention on climate change back in 1992, around the time that I was just finishing my doctorate, we had the Kyoto Protocol a few years later, which was supposed to implement the Rio Convention. We had Copenhagen Conference in 2009, which set the original goal of limiting warming to 2 degrees. The Paris Agreement in 2015, which you could argue was the first point where these agreements seem to be making some impact, at least we're sort of doing, we seem to be affecting the first derivative, at least, of the emissions curve. And then, of course, Glasgow, with Boris Johnson, seems to have, you know, undone the good that was done in Paris, I don't know. So and all this time, we've got people exhorting the world to follow the science, and it doesn't seem to be working. So I did physics and philosophy here, so I hope you'll indulge me. I know it's a physics society talk, but I'm going to treat you to a little bit of political philosophy. I don't know how many of you have read your Hegel, and to be honest with you, I haven't read my Hegel either. But I have read Francis Fukuyama's book, The End of History, which it had a huge amount of impact in the 90s. It was inspired by Hegel's political philosophy, the essence of which is that humanity is driven by a tension between three things. Desire for sort of gratification, basically, sort of, you know, pleasure, so to speak. Reason, where we sort of, okay, we know certain things we shouldn't do and so on, so we're not just purely desire-driven. And then something called thumos, which Hegel introduces to talk about, which he actually regards as the main driver of human history, really, of political development. And what is this? And Francis Fukuyama expands on this idea in his book, The End of History and the Last Man. So what is this thumos idea? So what it is what Hegel refers to it as the part of the soul that demands recognition. I think in modern parlance, you'd probably just call it respect. It's the desire of individuals to be recognized and valued, have their opinions valued. And again, inspired by Hegel, Alexander Kojève was a political philosopher in France in the 1930s and 40s. And he saw history as a gradual progress towards the end point, the end goal of a liberal democracy where basically the experts were in charge. What Nietzsche, a rather less pleasant political philosopher, would have referred to as the men without chests. And it's this sort of rule by nerds approach to climate policy that we've tended to adopt in telling people to follow the science. And what arguably this has done, no, at least this is what I'm asking you to think about, whether there's a side effect of this, has been that it's essentially denying the thumos of everybody else. Telling people, you don't understand what we're doing, so you'll just have to do what we tell you. You can't possibly understand our climate models because they're so complicated, so just follow the science. Do what the scientific, and we have elaborate processes like the Intergovernmental Panel on Climate Change, which is supposed to draw together all of this scientific evidence and tell people what to do about it. And so what I'd like you to think about is what can physicists do to help get back to what Hegel actually said was the desirable outcome, which was what he called isothemia, or equal recognition, which he contrasted, by the way, with megalothemia, which is when small numbers of individuals see success entirely in terms of elevating themselves above everybody else, which you might argue is kind of the situation we seem to be in at the moment. I won't name any names. But Hegel's ideal was where all people were equally recognized, their views were recognized. And how can we, on an issue like climate, where, of course, there is physics involved in understanding climate, how can we make sure that everybody's views are included in the conversation about what to do about it? I think that's a challenge for us. You know, the Paris Agreement, if you like, you could almost say it was the ultimate victory of the men without chests, the sort of the end of history for Francis Fukuyama, where it was a very technocratic process of negotiation that nobody was even remotely expected to understand that came up with the Paris Agreement. So, the solution, equations for the people. This is what I want you to think about. What can we do to expose our thinking more to the world that actually ultimately has to make decisions about what we do? You know, I often hear in conversations about making climate science more transparent, people often talk about making models open source. That's a very popular thing. Oh yes, of course, we're going to make our models open source. But we don't make our thinking open source. Or at least I think that's what we need to think about doing. How do we open source our thinking? By giving people, and open sourcing our thinking as physicists means thinking about how we can frame what we do, frame the essence of our reasoning, which is encapsulated in algebraic equations. How do we make that accessible to the people who want to make decisions on the basis of what we do? So let me, that's enough philosophy. Let me give you a couple of examples from my work. I've worked a lot with the Intergovernmental Panel on Climate Change, which oftentimes does feel a little bit like a physics and philosophy or philosophy tutorial, in that you'll sort of spend a lot of time agonizing over exactly which words you can use. And here's an example of one of those sentences that we, believe you me, we agonized over this sentence for many hours in a windowless room in Korea, this one was. And this is where we landed. This is the first time the Intergovernmental Panel on Climate Change tried to sum up in a single sentence what it would take to stop global warming. And this is where we got to. Reaching and sustaining net zero global anthropogenic carbon dioxide emissions and declining net non-CO2 radiative forcing would halt anthropogenic global warming on multi-decadal timescales. High confidence. Okay, so there's a lot there. But what sort of slightly frustrated me about this whole process is that we spent all this time agonizing over the words, when what we've done is spent a very long time using misinterpretable words to represent a very straightforward equation. Because if you look at what drives global temperatures on multi-decadal timescales, the change in global average temperature on that sort of timescale is driven by essentially three terms. Cumulative carbon dioxide emissions over that period, so the amount of carbon dioxide we dump in the atmosphere over that multi-decade period. It's a delta G because G is the total amount we've emitted since pre-industrial, so this is the additional CO2 we dump in the atmosphere. The change in global energy imbalance due to other climate drivers, things like methane, aerosols, nitrous oxide, over that period, and the average global energy imbalance due to these other climate drivers over that period. With these three terms, we can explain the behavior, and a couple of constants, three constants as well, which are uncertain. So those, the coefficients here, kappa E, kappa F, and rho F, they're uncertain, but we can pin them down to within a factor of plus or minus 30% or so, even just based on observations. We know how the world has warmed already, so we don't even really need models to pin these things down. And we can explain the behavior of coupled, I'll show you in a minute, we can explain the behavior of coupled ocean-atmosphere climate models remarkably well. And this was this point has been around for a while. It's certainly not new. I think this particular formulation was actually presented most clearly by Ashwin Sheshadri in 2017, but you can go back to Isaac Held's and Jonathan Gregory's papers back in the 2010s to 2000s and see the sort of precursors to all this thinking. And elsewhere in the IPCC reports, we have another example of a verbal equation. This one's even more sort of a mouthful, expressing methane emissions as carbon dioxide equivalent emissions using GWP 100. GWP 100 is just a sort of exchange rate that people use between gases to work out an aggregate carbon footprint of multiple gases. Overstates the effect of constant methane emissions on global surface temperature by a factor of 3 to 4, while understating the effect of any new methane emission source by a factor of 4 to 5 over the 20 years following the introduction of the new source. Again, very convoluted sentence, which actually, if you look at it really carefully, you realize is actually that same equation, just resurfacing. How can I say that? Well, look, methane is a short-lived gas. It has a lifetime, because it oxidizes naturally in the atmosphere, it has a lifetime of a decade or so. So if you switch on a methane emission source and keep it constant, the forcing, the energy imbalance at the top of the atmosphere that results from that methane emission source increases rapidly and then stabilizes. That's the yellow line behind me. And that's completely different from CO2. If you switch on a CO2 source, the energy imbalance due to that CO2 source just keeps rising because CO2 accumulates in the system, whereas methane doesn't. It's a short-lived pollutant, like most of the other pollutants, apart from nitrous oxide. Most of the other pollutants that we have to worry about on the climate issue are short-lived, meaning they've got a lifetime of a decade or less. And so, because we can, because the forcing due to methane, forcing is just proportional to the average rate. E sub s means it's a short-lived emission of a short-lived thing. That A is just a proportionality constant, roughly constant. We can do a quick substitution into that other expression, and you can see an expression for global warming in terms of emissions, but now in terms of emissions, so-called carbon dioxide equivalent emissions, using this conversion factor, that conversion factor A. I've just substituted in for the forcing here, for the change in forcing here, and the average forcing there I've substituted in for the emissions of short-lived climate pollutants. And so that's the change in CO2 equivalent emission rate of a short-lived climate forcer like methane, and that's the average CO2 equivalent emission rate. So I'm just substituting into the equation. And what this means is, if I look at the two parts of this equation, if I express a constant methane emission as CO2 equivalent, then, if you remember the IPCC sentence, I overstate its climate impact by a factor of 3 to 4. So you can infer, if you really think about it, from that convoluted IPCC sentence, you can actually start to work out what the constants are. Okay? So you can see because I'm expressing this as if it's a CO2, so that tells me that Ka rho F is Ke over 3.5. And sure enough, if we actually go and look at our best estimates of those constants, that's about what it is. And that's not a coincidence. It's because it was people like me who wrote that sentence in the IPCC report. We knew this equation. That was what was in our heads, but we didn't put it down. And I did actually, to be fair, I did argue at the time that we should include the equation, and I was kind of laughed out of court. I said, no, nobody will understand it. And I just don't believe it. I think we give up too easily in presenting the way we think in terms of equations. I was in Brussels on Tuesday this week, and they wanted me to give a presentation on their climate neutrality forum. I think they wanted to give me a presentation. We need to give them a presentation on, what balance meant in the context of the Paris Agreement. Article 4 of the Paris Agreement talks about a balance in greenhouse gas emissions and sources and sinks of greenhouse gases. And so I made a point of showing this equation and saying that this is what it means. And I spent 10 minutes just going through each term in the equation. And at the end, the chair sort of asked, does anybody think this is the kind of thing we could use at all in policy making in the European Commission? Everybody just laughed and said that's ridiculous. But so many of them came up to me at coffee and said that was really interesting. And I'd never knew about that term, or the rate constant. So they did understand it. But there's this sort of collective pretense that, oh, no, nobody understands equations. Yeah? And I wasn't even using calculus. I used big deltas. I mean, you can see there is, of course, a differential equation underneath this equation, but I've learned my lesson. I don't use, for you it would be fine, of course, but there are limits to what I inflict on the world. But anyway, to come back to how we can infer the constants here, so we've got these constants that's where the 3.5 comes from, the sort of overstated by a factor of 3 or 4. And then this other statement, the impact of any new emission source will be understated by a factor of 4 to 5 over the 20 years following the introduction of the new source. So that tells you that KFA, if that's the new source introduced here, then KE delta T is going to be 4.5, KFA is going to be 4.5 KE delta T. So you can work out that kappa FA is roughly 90, so 4.5 times 20, which it is. In fact, if you work it out, or if you look at the standard values of these parameters, and so it all sort of makes sense. So in effect, what we've done in that elaborate IPCC sentence is we've come up with a word equation. And yet, because we've turned it into words, we've kind of made it a bit muddling and made it possible for people then to start arguing over, I don't like net zero. And it's like, well, yes, if by allowing net zero to become a pair of words rather than what it actually is, which is a number, let's face it, and indeed, I can actually tell you very precisely where the phrase net zero came from. We were in the plenary of the IPCC fifth assessment synthesis report, and the way the Intergovernmental Panel on Climate Change works is the authors of the report, at the end of the report writing process, the authors of the report have to sit on a stage in a big conference center and get grilled by the world's governments or representatives of the world's governments to check that they haven't sort of, slipped in any political, agitation into the report, and that everything's nice and clear and is meant the way it's intended and all that sort of thing. And at one point, I was sitting next to Pierre Friedlingstein, who was a very famous carbon cycle scientist on the platform, and suddenly one of the governments put their placard up and said, in this sentence it says something about zero emissions. We'd like to say net zero emissions. And I remember Pierre he's Belgian. He's a very nice guy, very sort of avuncular sort of guy. And he said, "Well, it means the same thing." Yeah, I mean it does. As far as we were concerned, it meant exactly the same thing. So what Pierre said to me is, well, if it makes them happy, let's just, move on so we can go to the pub, Anyway, so that was the origin of net zero, hey-ho. Because it turned out, by sort of turning it into a phrase rather than a number, I think we probably should have fought harder against that one. Anyway, so if we'd have stuck to the equations, delta TS equals 0, no more warming, it's fairly obvious what that means. You can't really argue about it. And it has implications, and indeed if we sort of add back in some of the hidden complexity underlying this expression, you'll notice here what I've done is I've just gone back to the original formulation. That's additional cumulative CO2 emissions over that period, change in forcing, non-CO2 forcing, average non-CO2 forcing. But I put this term in, which is the fractional rate of warming if you stabilize forcing, and that in the CO2 term must be balanced by something else. And what balances it is that because we've put CO2 into the atmosphere, if we were to stop putting CO2 in the atmosphere, we don't get constant forcing, but the concentration of CO2 in the atmosphere immediately starts to decline, and it declines at a rate, rho e, which happens to be roughly equivalent to the rate at which the temperatures continue to adjust if we stabilize the forcing, and that's why if you switch off the emissions, you get constant temperatures. But it actually tells you what things, this gives you a pretty complete account of what it takes to stop global warming in terms of emissions. And it has sort of important implications of drawing your attention to what emissions need to mean in that expression in order for the equation as a whole to hold. And there's a whole other lecture on why actually certain policies that we have at the moment don't really fit with that understanding. It works. I mean, it doesn't work perfectly, but if you just take this simple, it's a two-term equation relating forcing to temperatures, and you can see it captures, this is the exercise here is we've fitted the parameters to the red lines and then predicted what happened in the blue lines, and to within the fuzz in the simulations. These are simulations with fully complex coupled carbon cycle Earth system models. We can predict what temperature they will peak at. It's sort of good enough, as I say, for government work. But instead of talking about this equation, what most of the conversation with policymakers and the public is about is sort of, do you accept the results of climate models, these huge, very complicated climate models, which people love looking at and saying, look, there's X, Y, Z wrong with this climate model, so I'm going to reject it, or I don't like these climate models. And we have, Breitbart articles like this one, and I feel strongly about this one because I was the climate alarmist who was apparently admitting we were wrong about global warming at one point, when we published a paper revising a number that was within the error bar of what the number was before, but because it was sort of revised downwards, apparently we were admitting we were wrong. If instead of, we've allowed what we do to be caricatured in that way, which perhaps wouldn't have happened if we'd have been clearer. No, we weren't wrong about the equation. We were just adjusting the constants. We were adjusting the things which we'd always acknowledged we didn't know in that equation. So that's the sort of physicist thinking about the physics of the problem. And but I'd like to sort of also encourage you to think about how we can apply physicists' way of thinking to other aspects of the climate problem. Because, you could argue that the relationship between emissions and global temperature is actually pretty straightforward and largely done, and there shouldn't be that much argument about it. And in fact, there isn't as much argument about it as there is about other aspects of the problem, such as how much damage climate change is doing. So increasingly we hear in the political conversation, oh yeah, we know that climate change is happening, but it won't be too much of a problem. It's actually not going to cause too much damage. And so again, how can physicists' way of thinking be used to inform that conversation? So it's no longer a conversation about physics, because it's about impact on the world economy, on ecosystems and all the rest of it. But how can we use the way we think, the way we reduce systems to inform that conversation? And typically, if you want to talk about the impact of climate change on an economic system, such as the entire world economy, or even a subset of the world economy, you come up with an expression that says, well, to first order, it's going to be because you're perturbing away from a pre-industrial equilibrium situation where the economy has adjusted, or the agricultural systems or ecosystems have adjusted to that pre-industrial equilibrium. Because you're perturbing away from it, you'd expect the impact to be some form of polynomial. The reason you'd expect it to be and you probably expect it to be a sort of second order or more than second order polynomial, because you know that as you move away from that pre-industrial equilibrium, you're going to get damage whether it gets warmer or cooler, because you're in equilibrium to start with. There's no particular reason to think that global warming would be better for you than global cooling, or vice versa. So, we've got only a couple of constants in here that you can start to have a conversation about the impact of climate change on the world economy. The loss due to the warming we've already observed, whatever that is, and then some parameter that determines basically how, does the damage to the economy drop off very rapidly, or does it drop off gradually? What we can't say about the cost of climate change is it's very hard to put an absolute number on it, because that's very sensitive to how you value things like poor lives versus rich ones. In fact, when you delve into economic assessments of the impact of climate change, you very often realize that actually they're assigning a much lower value to a poor person dying. And if you think that sounds horrible, if you think about the way economics works, the impact of a poor person dying actually does have less impact on the world economy than a rich person dying, okay? That doesn't make that logic sort of acceptable or moral in any way. It's just that's the way it works. Then there's the sort of, if climate change were to cause mass movements of people from poor countries to rich countries, how do you put an economic value on that? Very often, if people move from poor countries to rich countries, the global economic, GDP, global production actually increases. But the average per capita income in both the source country and the destination country can go down. I'll leave that as a little sort of conundrum for you to think about as to how that can be, okay? The hint is it tends to be the richer people in the poor countries who move to the rich country, and they tend to then be the poorer people in the rich country, okay? So anyway, then of course there's the question of, how do we value impacts on different generations, and how we assign a value to low probability global events. I mean, how would you assign a value to an extinction? You know, how do you put a number on that? These are really difficult questions to answer, and there aren't really correct answers. But what we can say about the cost of climate change is as we move away from those familiar conditions, we expect curvature, and you know, as you'll all know, if you know that something's a maximum, locally it's going to look quadratic. I mean, that's just what we typically find, unless there's some very, very good reason for it to do something different. And therefore, for small changes, and it's important to stress this is only really for small changes. If you get to large changes, we can't really say anything. We can make quite strong statements, not about the absolute impact of climate change, but the relative impacts of different amounts of warming. So if 1 degree of warming causes 1D damage, okay, then 2 degrees 4D, 1.5 degrees 2.25D, and at least this if it's a quadratic, so it might be more than quadratic. And so you can already say that the additional cost of 2 degrees of warming versus 1.5 is at least as high as the costs we're already experiencing at roughly 1.25 degrees of warming, which is where we've been for the past few years. So that's useful information to people, which we could have a conversation about. And I think it's a conversation we could have. It's only a quadratic, it's not a very complicated equation, but it's not a conversation that happens. We just have people saying, you know, Bill Nordhaus says the impact of climate change is X, and Bjorn Lomborg says it's Y, and they disagree with each other, and the conversation can't really continue without the equations. Finally, let's get on to doing something about climate change. This is where it gets really controversial, and where the rubber hits the road, so to speak, in terms of where the political disagreements come. These are to sort of illustrate net emissions of carbon dioxide in the scenarios that meet the more ambitious goal of the Paris Climate Agreement, limiting warming to 1.5 degrees. And you'll notice that many of these start their emission reductions in 2020, some of them even earlier than that. And of course, in case you hadn't noticed, we did not start emission reductions in 2020. But more worryingly, they always look a bit like sort of Wile E. Coyote scenarios. You know, emissions go along like this, and then suddenly they go off a cliff. They go round. There's a completely discontinuous change in the emissions at the point where climate policy kicks in. And you know, it looks kind of absurd, and it sort of is. And it means that people like Prince Abdulaziz bin Salman, who happens to be the energy minister of Saudi Arabia, when talking about a particular scenario that was extant a few published by the International Energy IEA, the International Energy Agency, a few years ago. It's a sequel of the La La Land movie, as he called it. Why should I take it seriously? He's saying this scenario is nonsense. Because he was talking about a scenario, he was talking about the output. He wasn't talking about the equations underlying it. And so it was possible, therefore, for him to completely dismiss it without really any further conversation. He just shut the conversation down. Scenario is ridiculous. Move on. So let's think about, you know, where these scenarios come from, and whether, again, we can apply the kind of physicist thinking that we really encourage in Oxford, which is sort of reducing everything to its absolute bare essentials so that you can, you know, solve a finals problem in 45 minutes. How are they constructed? Well, the basis of them is this idea of abatement cost curve, so what it costs to reduce emissions. And the idea that we introduce climate policy that it can be represented as some kind of price on putting CO2 into the atmosphere. So what does it take to reduce emissions? Well, according to Goldman Sachs, at least in 2019, this is just an illustration, it's a nice it's a nice colourful diagram, so don't take the numbers too seriously. Certainly don't take any numbers too seriously if they come from Goldman Sachs. But you could, you know, but it is consistent with the general view that if we were to impose a global carbon price of $100 per ton of CO2, that means if the world were to have some kind of carbon tax that said if you want to emit a ton of CO2, you'd have to pay $100 for the privilege of doing so, then about half of the activities that currently put CO2 into the atmosphere, about half of the CO2 we currently put in the atmosphere, would no longer make sense. And we just do something else instead. We'd substitute away from those. So let's think about the implications of this sort of scenario. Look at the shape of that cost curve, okay? As we reduce emissions, it goes along like that, and then it gets very, very steep, okay? So we're going to just parameterize that very simply and say the cost per ton of CO2 avoided is proportional to 1 over the residual emissions, yeah? So that gives you that rapid upward curvature. As emissions go down, it gets more and more expensive to get rid of the next ton. And if we just, do what an economist would tell you is the rational thing to do, you say you reduce your emissions until the benefits of avoiding the next ton of emissions are less than the cost of avoiding the next ton of emissions. So you sort of keep reducing your emissions until it's no longer worth reducing them any further. So if we do that, and remembering the curvature of the damage function means that the warmer it gets, the steeper that damage function, so the bigger the impact of adding 1 more ton of carbon dioxide to the atmosphere becomes. So the benefits of avoiding emitting that additional ton, they go up as we reduce our, the benefits go up as the world gets warmer. They also go up the more we reduce emissions, obviously. And the cost, I've just sort of given you a sort of simple schematic here where the cost goes up inversely to the remaining emissions. So as the world warms, we expect the benefits of avoiding go up because the curve is getting steeper and steeper. And so it makes sense as the world warms to reduce emissions, yeah? Because it's sort of more and more, there's a greater and greater incentive to avoid releasing the next ton. But where does this get us? So you can actually, if you sort of mull over it for a bit, you end up deciding that the warming over a multi-decade period that maximizes benefits minus costs is just inversely proportional to whatever temperature you've reached in that period. And if you gaze at that equation, you realize that actually the benefit cost maximizing solution in this scenario is to warm the world forever. Which doesn't sound very plausible, okay? So that immediately tells you there's something missing here, but okay. There has to be something missing, and the thing which is missing is that this graph behind me is only showing you the cost of avoiding emitting CO2 by replacing fossil fuels with other things. So that's what this means, substitution and conservation measures only. They've limited this curve only to replacing fossil fuels rather than dealing with the carbon dioxide they generate. If we take that curve, it's the same curve there just shown in red, and show on top of it what it costs to get rid of carbon dioxide after you've produced it, you'll notice that has a completely different shape. It sort of goes up more or less in a straight line as we increase the amount of carbon dioxide we dispose of. And you see they cross over around sort of 3/4 of the way to net zero. So after we've reduced our emissions by about 75%, it no longer makes sense to stop producing carbon dioxide at all. It makes more sense to get rid of it. And that's where the net in net zero comes from. So I showed you those scenarios of emissions earlier on. This is the numbers behind them. In red, the amount of carbon dioxide we produce in these scenarios from burning fossil fuels. And in blue, the amount we dispose of, which currently at the moment is 0. We dump it all in the atmosphere. But in these scenarios, we achieve what we call geological net zero by disposing of all the carbon dioxide we still generate after mid-century by putting it back underground. And if I just take those same scenarios and calculate a fraction, one minus CO2 stored over CO2 produced, they look like this. Okay, so why have I done that? Well, they don't look really any tidier than they did to start with. They still look like a bit of a mess of spaghetti. But if we reconcile the start dates and just shift the scenarios around so that they start reducing this so-called net geological carbon intensity of continued fossil fuel use at the same time, and then non-dimensionalized time, something that will be very familiar to all of you, by just saying instead of plotting year, we just plot fraction of time to date of net zero. Yeah, you can see what the horizontal axis is here. Suddenly they're all kind of the same shape. And they're kind of obviously a quadratic. Because, if you like, these economists have gone away and scratched their heads and run very complicated models and essentially rediscovered a geodesic. If you start here and you want to get to there and it's currently flat, that's the path you're going to follow. There's not that many degrees of freedom. So here's another suggestion of an equation, which is just simply the equation of that pathway. Time goes up quadratically. The stored fraction, as the stored fraction goes up quadratically over time, the fraction of CO2 that we capture, of the CO2 we generate from remaining fossil fuel use, if that goes up quadratically over time, we can actually use our progress in scaling up geological storage to predict when we're going to stop fossil fuels from causing further global warming. By the way, I'm way outside of the literature here. I'm making this up as I go along, okay? But you know, this is what you can do with just applying the kind of physicists' thinking we encourage you to do to these kind of big global problems. And so, if we take our progress, this is from the Global Carbon Capture and Storage Institute report from last year. They're predicting that by 2030, the stored fraction will reach 1%. We'll be putting 1% of the carbon dioxide. It's currently about 0.1%. They're predicting we'll get it to about 1% in 2030. And depending on exactly where you choose for the time origin, you might say that's a sort of acceleration of roughly 0.08% per year over the next 5 years. Okay? Okay, inferring an acceleration from the first 2 data points of a very noisy series is a pretty brave thing to do. So let's not over-egg this. But if we maintain that rate of acceleration in the stored fraction, we immediately have a prediction of when we're going to stop global warming. Not by 2050, I'm afraid, sorry to disappoint you, but in about 50 years. Which interestingly, and this gives me some sense of powerful vindication in this line of thinking, is in the summer of last year, a group of Chinese scientists, I have no doubt with the blessing of the Chinese government, published a scenario showing global emissions, what they called a plausible global emissions scenario, implication being none of the other ones were, which ended up with about 2 degrees of warming and, interestingly, reached net zero in 2075. So I enjoyed giving this talk in Beijing, and they were sort of like, yeah. So here we are. Instead of arguing about models and saying whether we do or don't like them, could we change the climate conversation by encouraging people to talk about equations and reducing the way we think to as stylized and simple equations as possible so that we can have a conversation about them? You know, rather than Kemi Badenoch saying, you know, I don't believe in net zero, I'd rather we had a conversation, okay, what do you not agree with in the equations behind me? Which of the parameters do you think I've got wrong? Which of the equations do you think I've got wrong? Do you think that climate change, the damage from climate change will do that? Really? Okay, how's that going to work? You know, let's discuss it. It brings things out in the open, it exposes the world to the way we think, and I think it could actually help make politics a little less toxic. So that's what I'm encouraging you to think about, is that you have a duty to teach the world to think as physicists and make the world a better place. There's a challenge for you. Thank you.
Thank you very much, Myles, for your talk. That was really engaging and inspiring. We have around 30 minutes for Q&A, so if anyone has any questions, please raise your hand.
So a lot of this comes down to a communication problem in the way reports are written. How much of that do you think comes from the requirement for the reports to be written in a unanimous fashion of all the parties? And therefore, how much do you think this might be improved by some of the newer conferences that seem to be happening, which will not require unanimity?
I actually don't. I think we could get unanimity on. I actually think the unanimity requirement is healthy. I think it. At the end of the day, we would not have got the Paris Agreement without the IPCC process. And yes, the US has flounced out of the Paris Agreement, but the US is doing a lot of weird things right now, and they'll be back. And we definitely don't help matters if we just sort of have lots of competing processes. But what I think we can do is get, if we were braver as physicists about saying, no, this is how we think, this is the equation we're using here, let's talk about it, I think we might actually find getting consensus easier. But it's surprising, as that experience in Brussels suggested, it's surprising, there's surprising resistance to that. And we can speculate about why that's the case. Maybe it's because if you've got an equation, there's nowhere to hide. Yeah? Maybe lawyers don't like equations for good reason. They can't fudge them.
So I think a lot of the issues with showing people equations isn't that people can't understand it, obviously they can, but it's that they don't think that they can. So how do we convince people that they can understand maths actually?
I spent a lot, yes, that is such a good question. I don't know, I wish I knew. Partly by, one thing I've discovered is that if people have an incentive to understand maths, they do. Yeah, if you're, and indeed, as I think somebody once quipped, nobody will ever understand something if their livelihood depends on them not understanding it. Yeah, so I think what we need. So I presented the methane discussion is particularly relevant to livestock farmers, and I once did an interview with Farming Today, and I actually insisted. I said I'll do the interview, but only if you let me give the equation, and that was the most downloaded episode of Farming Today of that year, and 20,000 farmers around Britain downloaded it, played it several times over, worked it out, and then wrote to their MP complaining they were being diddled. They got it very quickly. So when people want to understand something, yeah, calculus takes a bit of time to bed in, but these kind of equations, yes, they can do them, and it is a lot of it is just a matter of just sort of reminding people that what they can do. It is very difficult, and when you get out there, and you should get out there and try and be brave about showing people's equations, but also you've got to remember, you've got to get feedback, and a lot of things will really catch you out. For example, I was recently caught out by presenting an equation, and I'd forgotten that when you say AB, you mean A times B. I was leaving out the multiplication sign. I mean, how many of you would have thought of putting the multiplication sign in there? But for that audience, I had to remember. So that's, but that was just a convention. It's easily fixed. So you can very easily lose people, but it is fixable, and we can bring people on. We've got to try, because, otherwise we're not really, as I say, we're not really open sourcing our thinking. And we should.
Yeah, my question is kind of like a follow-up question to that, because my research is in politics and policy, so I'm more concerned about how we can...
Well, I hope I got my Hegel right.
So my concern is more about how we can translate this into concrete policy support, because, I mean, conveying scientific truths about climate change is important, but how you can really convince people to sacrifice, to pay price, to do the right thing. Because knowing something is right is one thing, but how you can convince people to do the right thing is another thing. Just take an inappropriate example. I know organic food is good, but every time I go to the supermarket, I still buy cage dye, because that's cheaper, right? So knowing climate change is happening, we can convince this message to the public, but how we can convince them to pay a price, to sacrifice, to really do something to deal with climate change?
Well, there's nothing in these equations that says what's the right thing to do. They don't tell you that. They just tell you the framework we're thinking on, what we're thinking in order to decide what's the right thing to do. And so I guess I'm not suggesting necessarily that these equations would result in more ambitious climate action. That's not what my main priority here is to detoxify the debate. Whether the result of that, I suspect that if we were to detoxify the debate, we would get more ambitious climate action, but that's not the point here. The point here is to let everybody join in the discussion about how fast we want to act, how much we value what's happening, and so on. And so I don't see what I'm advocating here as, in some sense, it's the opposite of trying to persuade people to act in a particular way. I'm trying to make it easier for people to make their own minds up about how they want to act. And I think we have to accept that sometimes, having given people these equations, they may look at them, they may understand them, and they may decide, no, I don't want to reduce my emissions. I don't care about my grandkids. It's let the world warm. If they've made that decision fully in the knowledge of the implications of their decisions, that's the way it goes. I don't think, we don't have any right as physicists to tell people what to value. And that's where it's problematic where we are now, because the conversation is sort of coming out from an elite to tell everybody else what to do, and everybody else is rebelling against it. I happen to be quite confident in people. People probably do like their grandkids. When people do, when experiments have been done with people, when people really understand what's going on, they tend to end up in a pretty ambitious place. But we have to trust them. Trust them with our thinking.
May I ask, how did you get into climate physics?
How did I get into climate physics? So as I say, I did physics and philosophy here, but it was in the 80s. This was not an issue. And it was just after I finished my degree here, I was working in East Africa in saving trees. It was working for an environmental NGO, but I did an assignment for the UN Environment Programme, and the climate topic was coming up, and my boss in the UN Environment Programme said, because at the time I was sort of thinking of a career in development and so on, and he said, for heaven's sakes, if you've got a physics degree, go use it. Idiot. More or less, those were his words. So I came back and did a doctorate and haven't changed since. So yeah, so I definitely came to it. These days, there's two reasons you can come to it. It's a very interesting topic, but I definitely came to it from a view of sort of understanding the issue and contributing to understand the issue, which is why I've spent a lot of my career arguably not really thinking about the sort of very complicated challenges in understanding how our weather is changing and so on, but how can we make these very complicated things laughably simple? And when I look at what I've done, I've had far more impact when I've, in view of many colleagues, oversimplified things. than I have when I've made them more complicated. I'm not saying that complexity is not valuable. Of course it is. And it is a very, very complex system. But we also need simplicity in the conversation.
What kind of strategies do they have to reduce the amount of CO2 in the atmosphere?
To actually lower it.
Yeah.
I mean, technologies exist to do that. It takes energy and costs money. And it's much easier to burn fossil fuels and take CO2 out of the ground and dump it in the atmosphere than it is to suck it back out again. In fact, Oxford leads the CO2 removal program of the UK. So we've got a whole program on different technologies out there to capture CO2 back out of the atmosphere. The difficulty you've got is a fundamental thermodynamic one. Once CO2 is in the atmosphere, it's dilute, 0.04% of the atmosphere. And so there's a thermodynamic limit to how much energy you need to re-purify it in order to dispose of it. Once you've got a pure CO2 stream, it's actually relatively cheap and straightforward to get rid of it. You just stick it back underground. If you stick it deep enough, about a kilometer deep, it diffuses into the rock and stays there indefinitely. But it's getting that pure CO2 stream in the first place that's the challenge. And there's some great chemistry and physics to be done in that space, and we need it. We're going to need to get rid of a lot of CO2 this century, and whoever cracks the cheapest way of doing that is going to do very, very, very well. So good luck.
So obviously spin is very, very common with these things, like that news article saying that you've gone back on your thing when actually you just revised it. So what makes you think showing people these equations won't also just become a victim to political spin?
I'd like to challenge them to spin an equation. I just think it's harder. I don't know. It's an experiment. Look, I've not done it, have I? I mean, and who knows? I'll need your help. Because it's certainly not something I can do on my own. But if we try and, because this is how we think. So we're only being honest with people in giving them the equation, and we're sort of removing the suspicion that people have. So, what's your agenda here? You know, I think that a lot of times, you know, when I'm introduced as a climate scientist, you can see sort of certain people, oh, he's gonna take away my gas boiler, you know, so that's why I think we need it's about, I don't know, I'm sure somebody will try and spin an equation, and good luck to them, but I just think it's harder to spin an equation than it is to spin words. The English language is horribly slippery. Look what happened to net zero. As I say, Pierre and I thought this was totally unambiguous, like what's the problem? The zero, net zero, if it makes them feel better, as he put it. You know, and we were badly wrong on that one. So whereas, you know, an equation, you know, every term in it has a meaning. You can debate exactly how to define it and so on, but it's harder to, I don't know. As I say, I've never seen a spin doctor try and spin an equation, but that's the challenge we want to give them.
Yes, my question is, when you want to convey something like this to the general public, how do we communicate it in a way that makes it actually feel immediate to them, make it feel relevant to them? Because I feel like a lot of people tend to try and overlook a lot of issues just because they don't think it's immediately relevant.
So, absolutely. Again, emphasizing, I always try and avoid, and I often actually say in a talk, I'm not telling you to do anything. Yeah, and so I don't go into a presentation on climate change with a view to encouraging my audience to behave in a particular way. My job is for people to understand what's going on. And things like, you know, really simple facts like the amount of climate damage that we're experiencing already is similar, at least, to the amount that we're likely to see between 1.5 and 2 degrees of warming. People find that helpful, I find, because the difference between 1.5 and 2 degrees of warming is like, the temperature varies by much more than that in the course of a day. So what does this mean to people? I mean, it doesn't, as you say, it doesn't have any salience to people. So that's why I think, again, explaining the logic of these very stylized equations actually can help people sort of appreciate what's going on. Whether it'll encourage them to do anything, I don't know. As I say, time would tell. But there's only one way to find out. We have to do the experiment.
Thank you for the presentation. I'm just trying to figure all this out as well, same as you. But you mentioned that you're not here to persuade people into a certain kind of action. You're not here to change their behavior in a particular variance. But I mean, coming back to the start of the presentation, you mentioned that the reason why scientists had so much influence and then was subsequently ridiculed almost was precisely because they were doing projects that explicitly were intending to help, let's say, the society as a whole. And so I wonder if seeing as the common reaction to this kind of information is inaction, I just feel like would it not be valuable for scientists, physicists, let's say, to begin from a position whereby they are trying to persuade people into a certain behavior. And if it just so happens that, for example, in your case, you're simplifying complex models or changing the paradigm models into something more digestible, that itself is reflected that you are trying to persuade people.
I mean, obviously, I'm trying to persuade people to think sensibly about climate change. For many people, that would be a behavior change. Yeah, I mean, as opposed to thinking unsensibly about climate change. So, yes, obviously, it's not true to say that I just sort of issue words and I don't expect any reaction. There is obviously you are hoping to change things, and this whole the whole question, it's a bigger question really about to what extent scientists should take a position. During the pandemic, there was a lot of, should scientists come out and say in favor or against lockdowns and that sort of thing. And, as you may or may not recall, Oxford was right in the heart of that. There was a sort of big beef between Oxford and Imperial about, the value of lockdowns. And actually, I thought that was quite a healthy example of how science works, but that wasn't the way it came across to the public. It came across to the public as anyway. It's an interesting story, and I do think, by the way, it's a story that would have been helped with equations, because basically both teams were using the identical equation. They were differing in certain parameters in it that were rather obviously unknowable. So, there wasn't really any fundamental disagreement. There was just sort of, well, where are you on the spectrum here? And I think, again, if we'd have used the equations more in the communication, it might have been easier. And we also, by the way, we also need to be quite creative in how we explain equations to people, because sometimes, algebraic symbols don't work. So sometimes you've got to either use, so for the farming example on Farming Today, I used numbers because for many people, doing maths with letters is already a step too far. So you've got to be very flexible in how you present the maths, and that's often the biggest challenge here, is trying to work out, what's the maths that will work for the people you're talking to. And not being too sort of arrogant and saying, well, they should just learn my maths, I use calculus, so they should just get over it. Yeah, no, that doesn't work. So we have to lean in and work out what resonates for people. But I think we can try. It's an experiment I'd like you all to think about in your conversations. Try and use more equations. Use them all day in your physics. But do you explain things? Do you explain physics with equations on beer mats in pubs to people? Maybe we should do more of that. See what happens. Maybe you'll be thrown out of more pubs. Who knows? Not in Oxford, I hope.
So at Oxford, we did a presentation, it was a technical where they were talking about UK emissions. And they were saying that UK emissions have been going down, and for example, coal prices have been going down, and so things would automatically lead to the problem we solve in that way automatically, and those kind of things. And also, like, I talk to people here saying things like, it doesn't matter what Trump is doing, it matters what China is doing, India is doing, so those are some questions through the equation.
Well, just this is a good example of actually where these equations are. So they brag about UK emissions going down, okay? But the answer to that is, what's AG for the UK? Okay, how fast are we increasing the fraction, how fast is the fraction of the carbon dioxide we still generate from using fossil fuels that we capture and put back underground? How fast is that fraction accelerating? How fast has it accelerated over the past 20 years while we've been talking about this? And the answer is a big fat 0. Okay, so there's certain things the UK is not, we are now saying, don't worry, we are going to get our act together and we are going to, always in the future, actually do something about this. But that's why, you know, the fact that UK emissions are coming down and we brag about the fact that our emissions per head are lower than they were in the 19th century, all that really tells you is they were stupidly high in the 19th century. I mean, it's not, you know, there's a lot of illusory progress. And that's why, again, I think if we drill down to these equations, we can actually sort of separate the spin from the reality, or at least it may help separate the spin from the reality. I hope so anyway. I'm conscious that people, I know there's more, I hate cutting off questions. I just hand over to the chair. Did you want to ask a question at the back there? I'm sorry, let's take a last question and then we'll wrap, yeah?
I just wanted to ask, so you're talking about making maths mathematics more accessible for like the average person, basically, like from what I understand.
Well, it's not just to the average person, it's to everybody. Yeah, that's the point. And okay, so that includes the average, but the average person doesn't really exist. Yeah.
I was just going to ask, do you think there's also a lot to play with like education in terms of like how maths is treated and taught, like at a more elementary level?
Maybe, but actually, I can't remember who said. Yeah, I think it was you that said it. Most people actually understand much more maths than they admit. And I think that's my experience of it, is that people tell you, oh, it's maths. I gave that up at 13, you know? But then when you actually talk to them, you realize, yeah, of course everybody understands maths. I mean, we do maths all the time. That's how our brains work. We may not use the same symbols, but that's a matter then for us to work out what are the symbols that work for the person I'm talking to here. And so, you know, when Rishi Sunak got onto a sort of thing about how we've got to keep maths going till 18, I was sort of, you know, I could see the logic of that, but I wasn't sure that that was actually the solution. The solution is not to, you know, take everybody to insist that everybody keeps maths going till 18, but just remind everybody that when you stop studying maths, you're still using it, and you just sort of keep a general familiarity with mathematical concepts going for everybody. And that's really what we need to do. But it's a real challenge. As I say, it's an experiment. Let's give it a go.
Thank you very much, Myles, for your fascinating talk and answering our questions. And thank you everyone for attending. If you have any further questions, please feel free to come down and ask Myles at the front. There's also pizzas waiting in the foyer. Please join me for another round of applause for Myles.